Somewhere out past everything humans have ever mapped, a spacecraft roughly the size of a small car is drifting through territory no probe has ever visited. It isn't new. It isn't advanced by today's standards. It was assembled before personal computers existed, before most of the scientists now studying its data were born, and it survives on about 4 watts, less than the bulb in a refrigerator. That machine is Voyager 1, and what it's radioing back to Earth right now is unsettling physicists in ways that go well beyond interesting. The mission never should have lasted this long. Voyager 1 launched from Cape Canaveral on September 5th, 1977, with a plan that sounds almost quaint by comparison to what actually happened. Fly past Jupiter, fly past Saturn, snap some photos, gather some readings, then go silent. NASA figured the whole thing would wrap up by the early 1980s. It didn't. Voyager 1 reached Jupiter in 1979, capturing humanity's first close-up look at the planet, then swept past Saturn in 1980, using each planet's gravity as a slingshot to pick up speed and push further out. By the end of that decade, it had already become the most distant human-made object ever launched, and it kept talking to us the whole way. Then, in 2012, 35 years after launch, it crossed a line few people had even heard of, the heliopause. Picture the sun constantly exhaling a stream of charged particles, the solar wind, which inflates a vast protective bubble around the entire solar system. Every planet, every asteroid, every spacecraft we've ever built sits inside that bubble. The heliopause is the outer skin of it, the point where the solar wind finally loses its push against the pressure of interstellar space. Cross that line, and you're no longer in our solar system. You're somewhere else entirely. In 2012, Voyager 1 crossed it. For the first time in history, something we built was physically outside our home system, sitting in the space between stars, and still sending data back. That fact alone is worth sitting with. We have a living instrument parked in interstellar space right now, not near the boundary, not approaching it, inside it. No ground-based telescope, no orbiting satellite, no theoretical model has ever had that vantage point before. And what that instrument is reporting doesn't match what decades of careful, peer-reviewed science predicted it would find. For years before Voyager 1 got there, physicists built detailed models of what interstellar space should look like. Cold, thin, mostly calm, a quiet corridor where particles drift and not much happens. Voyager 1 arrived and found something closer to a storm. Starting in 2017, its plasma wave instrument began picking up a strange, steady signal. A faint but persistent hum running through the interstellar plasma that nothing in the existing models accounted for. Not a one-off spike. Not sensor noise. A continuous emission, present year after year, detected across more than 900 million miles of space. Roughly 10 times the distance between Earth and the Sun. Researchers publishing in Nature Astronomy laid out the conclusion plainly. Interstellar space isn't the smooth, uniform void scientists had assumed. It has structure, at scales from a few meters to millions of miles. It's turbulent. It's active. And we only know that because, for the first time ever, we had something sitting inside it to listen. Every model of what lies beyond our solar system had been built from the outside. Telescopes, math, inference. Now, the first instrument we've ever physically placed out there is telling us those models missed something real. And as the next part of this story shows, that isn't just an abstract correction to some textbook. It reaches back here, to the shield that keeps dangerous cosmic radiation away from every living thing on Earth. Here's the part of the story that stops being an abstract curiosity about a boundary billions of miles away and becomes something that touches Earth directly. The heliosphere, that bubble of solar wind surrounding our entire solar system, isn't just a scientific curiosity. It functions as a shield. It's what keeps the most energetic and dangerous cosmic radiation, the kind produced by distant supernovae, from slamming into the inner solar system at full strength. Voyager 1's readings suggest the environment pressing against that shield from the outside is more turbulent, more variable, and more energetic than any existing model accounted for. Nobody is claiming we know exactly what that means for the long-term durability of the shield itself. But the fact that serious researchers now have to ask the question changes something about how we think about our own exposure as a species living inside that bubble. And the story of how we're still getting this information at all is its own kind of drama. In 2023, Voyager 1 nearly went silent for good. For roughly 5 months, the spacecraft kept transmitting. But what came through was garbled, unreadable static that even JPL's most experienced engineers, people who'd spent decades interpreting this spacecraft's every signal, couldn't decode. The carrier signal was fine. The content wasn't. The cause turned out to be almost absurdly small. A single memory chip inside the flight data system had degraded after nearly 5 decades of relentless cosmic radiation exposure. That one failing component, a fraction of an inch across, was corrupting the formatting of every scientific transmission leaving the spacecraft. Normally, you'd fix a broken part by replacing it. That wasn't an option here. Voyager 1 sits roughly 15 billion miles away in a radio signal, moving at the fastest possible speed in the universe. It takes about 22 hours just to reach it. Every diagnostic attempt required a minimum 44-hour round trip. Send instructions, wait nearly a full day, receive a response, analyze it, adjust the theory, send new instructions, wait again. Do that for months, and you get a sense of the process JPL's engineers went through. Remote surgery on 1970s hardware, performed at the speed of light with a built-in day-and-a-half delay, where a single miscalculated command could end the mission permanently. They didn't rush it. Slowly, methodically, over months, the team figured out that the corrupted code couldn't be repaired in place, but it could be moved. They split the affected software into smaller pieces, relocated each piece to working sections of the spacecraft's limited memory, checked each piece individually, and reassembled the whole system so it worked correctly from its new home. By mid-2024, Voyager 1 was transmitting clean data again. And almost immediately, it resumed sending back more evidence of the same unexplained plasma disturbances that had puzzled scientists since 2017. More proof of a turbulent, structured interstellar environment that no model had anticipated. The spacecraft that was supposed to die in 1981 had just come back from what could easily have been a permanent silence, and it came back with more to say. But even that recovery, remarkable as it was, doesn't compare to what Voyager 1 actually found the moment it first crossed into interstellar space back in 2012. A discovery that reads less like routine physics and more like something out of the realm of the genuinely uncanny. For decades, physicists modeling the heliopause pictured a gentle handoff between two regions. Solar wind thinning gradually on the inside, interstellar medium gradually taking over on the outside, something like a river easing into the sea. Voyager 1's actual measurements told a very different story. At the boundary, particles weren't calmly fading out. They were colliding at extraordinary speeds, generating temperatures approaching 30,000 degrees Celsius. Not inside a star, but at the literal edge of our own solar system, in a region theory said should be cold and sparse. Some researchers have described this zone almost like a wall of intense energetic particle activity, a genuine physical barrier sitting at the edge of everything humans call home. Then came the magnetic surprise. Standard models predicted a clean separation at the heliopause. The sun's magnetic field on one side, the galaxy's entirely separate magnetic field on the other. Two distinct systems meeting but not mixing. What Voyager 1 actually detected was different. The magnetic fields on both sides of the boundary appeared to be connected, interacting through a process called magnetic reconnection, where field lines from different sources rearrange and release energy. In other words, the solar system and the surrounding galaxy aren't magnetically isolated from each other. There's an active exchange of energy happening at that boundary, a dynamic relationship no pre-Voyager model had anticipated. That's not a small footnote to append to existing theory. It's a signal that our picture of how the heliosphere protects Earth over long timescales needs real reconsideration. Which brings the story into the present. In 2026, that story isn't finished. Arguably, it's entering its most consequential chapter yet on a tighter clock than most people realize. Earlier this year, NASA made a decision nobody on the mission team wanted to make. The low-energy charged particle instrument, one of the few instruments that had run almost continuously since 1977, was switched off. Not because it broke, because there simply wasn't enough power left to keep it running. Voyager 1 draws power from 3 radioisotope thermoelectric generators, essentially containers of decaying plutonium-238 whose heat gets converted into electricity. At launch, they produced roughly 470 watts. Today, nearly 5 decades later, output has fallen to around 250 watts, dropping by about 4 watts every year. Sometime in the early 2030s, that output will drop below what's needed to run any instrument at all, and the spacecraft will go permanently silent. The mission team has planned for this for years, carefully sequencing which instruments to shut down and when, trying to squeeze the maximum scientific return out of a shrinking power budget. Of the 10 original instrument packages, 7 are already offline. Each shutdown decision is essentially a decision about which questions will simply never get answered, because there's no way to switch an instrument back on once it's off. Except, apparently, the team hasn't entirely given up on buying more time. And that attempt is where the next part of this story picks up. Here's a detail that hasn't gotten much attention outside the small circle of engineers actually working the problem. NASA hasn't simply accepted the countdown to silence. Teams at the Jet Propulsion Laboratory have reportedly been developing an experimental approach to redistributing power across Voyager 1's remaining systems, trying to squeeze additional electrical capacity out of components running below their theoretical efficiency. It's a risky idea by nature. Making changes to how power flows through a spacecraft built in the 1970s, with no possibility of a manual override or in-person repair, carries real potential for unpredictable consequences. So engineers have been testing the approach first on Voyager 1's twin, Voyager 2, which has somewhat more spare power margin and sits closer to Earth, meaning a failure there would be less catastrophic to the overall mission. If those tests go well, the same technique could eventually be attempted on Voyager 1 itself. And if it works, there's a real possibility. Not a guarantee, but a real one, that an instrument already shut down could be switched back on. The team isn't promising anything, but given how many times this particular spacecraft has already outlived every expectation set for it, nobody involved is ruling it out either. And there's a milestone already locked into the calendar, independent of how any of these power experiments turn out. Later in 2026, Voyager 1 is set to cross a distance of exactly 1 light day from Earth, far enough that a signal traveling at light speed, the fastest anything can move, takes a full 24 hours just to arrive. Send an instruction on a Monday, and you won't know whether it even reached the spacecraft until Tuesday. You won't hear back until Wednesday. No human-made object has ever been that far from home before, and Voyager 1 will cross that threshold while still alive, still transmitting. After that, distance and delay just keep growing. Every hour adds roughly 38,000 more miles between the spacecraft and Earth. Power keeps declining. At some point in the 2030s, the last signal will arrive. And when it does, the spacecraft doesn't stop. There's nothing out there to slow it down. No atmosphere, no meaningful friction, no gravity strong enough to meaningfully redirect it. It simply keeps moving in a straight line, indefinitely, carrying something remarkable along with it. Bolted to Voyager 1's frame is the Golden Record, a gold-plated copper disc holding greetings recorded in dozens of human languages, natural sounds like rainfall and ocean waves, roughly 90 minutes of music spanning many cultures, diagrams outlining basic scientific principles, and a map showing our location using the positions of pulsars. Carl Sagan, who helped assemble it, once called it a message cast into the cosmic ocean. That's exactly what it is. Long after the spacecraft itself goes quiet, long after every human structure and record on Earth has eroded away, that record keeps traveling, carrying proof that something curious once existed here, reached outward, and tried to say hello. Come back to the science for a moment, because there's one more piece of this story that deserves real attention. The mysterious plasma emission Voyager 1 has been detecting since 2017 isn't just a strange anomaly sitting in a dataset somewhere. Researchers studying it describe it as the first continuous, real-time measurement of interstellar plasma density humanity has ever obtained. Before this signal appeared, scientists could only capture scattered snapshots of interstellar plasma, usually triggered by specific events, like shock waves from solar eruptions that eventually rippled out past the heliopause. Useful, but sparse. Something like judging a continent's climate from a single thermometer checked once a year in one city. What Voyager 1 is providing instead is closer to an ongoing feed. A continuously updating picture of interstellar plasma as the spacecraft physically moves through it, day after day, year after year. That picture reveals space between the stars isn't the flat, uniform backdrop long assumed. It has texture, structure, and something close to weather. Patterns built from charged particles and magnetic fields spanning millions of miles, interacting with our solar system's boundary in ways ground-based models never predicted. There's still an open scientific question sitting at the heart of all this. Researchers have narrowed the persistent emission down to 2 possible explanations, but haven't yet determined which one is correct. One possibility is that it comes from thermally excited plasma oscillations, a real and interesting finding, but one that fits comfortably within existing physics. The other possibility involves a different mechanism known as quasi-thermal noise, which would carry information about plasma density and temperature in a meaningfully different way, one that would require real revisions to current models of the interstellar medium. Settling that question requires either more data from Voyager 1, which is producing less of it every year as instruments get shut down, or an entirely new mission purpose-built to study interstellar space. No such mission currently exists or has funding. Even if one were approved and launched immediately, it wouldn't reach the heliopause for at least another 25 years. Which means when Voyager 1 eventually falls silent, this particular question stays open. The unique real-time window it opened into interstellar space closes with it, likely for decades, possibly longer. That silence isn't a maybe. It's a matter of when, not if. Every year the power output drops a little more. Every year, another instrument gets switched off to preserve what's left. Somewhere in the early 2030s, the last functioning instrument will fall below its minimum operating threshold, and the final signal will begin its day-long journey home. After that, nothing. Just the spacecraft, continuing on at roughly 38,000 miles per hour, carrying its golden record deeper into regions of the galaxy that human explorers, if any ever follow, won't reach for tens of thousands of years, still completing a journey that started with an engineering team in 1977 who expected it to last 5 years. Here's the detail worth sitting with as this story wraps up. Right now, in 2026, the only functioning scientific instrument humanity has ever placed in interstellar space is nearly 50 years old. It was built with technology that predates personal computers, powered by less electricity than a kitchen light bulb, and it's actively reshaping how scientists understand the universe and our position within it. We've since built larger spacecraft, more powerful ones. Missions that cost vastly more and use far more sophisticated technology. None of them have told us what Voyager 1 has told us, because none of them share the one quality that actually made this possible. They haven't lasted long enough, or traveled far enough, to physically get there. Some questions about the universe simply can't be answered from a telescope on the ground, a satellite in Earth orbit, or a probe visiting Mars or the asteroid belt. They can only be answered by something that has actually crossed the heliopause and entered the space between stars. Right now, we have exactly one such machine, aging, running low on power, and still, for now, talking to us. Its signal is still arriving, stretched across roughly 15 billion miles, delayed by about 22 hours of travel time, describing a universe that turns out to be stranger, more turbulent, and more interconnected than any Earth-built model ever managed to predict. One small machine, a handful of watts, and a narrowing window to keep listening before it goes quiet. Possibly for a generation, possibly longer, until whatever mission eventually follows, it finally reaches the same boundary decades from now. Whether anyone continues paying attention while that signal is still coming in is, at this point, really the only open question left.